this mathematical object, which is like a series of shapes, and my JavaScript that I've left off. So, to recap, what I did is I generated the canvas so that it fills with pixels or image units, and which I got them to color them in a different way based on the row or the column number. I just looped it and I used the row and column number to get the color. So I've got that tested, so that's good. Now I'm gonna code the whole Mandelbrot set. So let us begin. So as we have the canvas, what I'll now do is generate the equation of the Mandelbrot set. So let's do that. So recapping that, if you do not know, the Mandelbrot set is based on an iterative formula of complex numbers. So let's create a class called coordinate, and I will just use this class to generate coordinate numbers with complex numbers. Trying to do is create a class that I can hold complex number coordinates, in which I will use to generate objects that represent coordinates that I will use, in which I will then pass into a formula that I will make later to generate the Mandelbrot set. And this formula is basically iterative. You get the result of a previous one, and you plug into the next to the formula, and you get that result, and you iterate it over again. So this is the equation of the Mandelbrot set. Anything complex squared, and then c, which is your initial coordinate. I'll code that later, and I'll create toString. So if you square coordinate, it will be using, it's like squaring a binomial in math, in which you use FOIL. But with complex numbers, if you square the complex part, the imaginary component, you'll actually get a real result. So let's say that x is your main coordinate, your real number, and y is your imaginary component. If you square the real number, you will get the real component squared, which is normal. But if you square the y, the imaginary component, you'll actually get a negative result. Because if you do this, if you do yi to the power of 2, numbers represent this one. This is the real number, and your I component will also be the ones that your results that you'll get from your foil, the outers and inners. I mean, so 2x plus y, I guess. I think that is what you'll get. 2 times x plus y, or something xy. I think it's not x plus y, it's xy. Alright. So I will probably return new coordinate in which, yeah, this dot x times this dot x minus and I'll create, so that's squaring a coordinate. Now I'm gonna do is add a coordinate. And I'll call this function to add c, which is like your initial coordinate. Not y, it's I. I should have done, it's not y, it's I. Because I normally use y for my y-axis, but in this case it's I. Because the y part is your I component. Alright. Now I'm gonna do is test it. I'm gonna test this part a bit. So, in this case, I will just create a new coordinate. And also in a toString, I'll have to append I because here the second component is the imaginary part. Let's try that. Got my developer tools and I, and then minus 2i, so yeah. So that's cool. So what I'll do is now test adding coordinate. Let's say I added this one with this. I should get 4 and 5. No. So that sucks. That's not a good thing. It turns out I get not a number, which is what I do not want. And yeah, there is a typo here. And yeah, I didn't put a space here, so that's kind of a thing. And now I should be getting something else. No, I didn't even use this formula. I don't know, I've been making a lot of mistakes all over the place, so. Oh, I didn't I should make another coordinate. Let's do that. Add. This one takes an input of another coordinate, so not a point. -3, I think that's the ones, and I should get something 4 and -5i. So that's what I wanted. Now let's try squaring it. Let's try testing the square method. I don't need that. Square coordinate. So let's do this one. I'm gonna use this and square it. I'll get a new coordinate once I call this, and I use the return coordinate and call it toString. So let's see if I get it. I is undefined. That's not good. That's not what we want. So this is a problem. So I is it square coordinate. Oh yeah. I didn't do the 2xy or something. It's still not a number. That's not good. Oh yeah, I called it y again. How silly. Alright. Let's do that. And let's see. 3 minus 4i. If I square it, I should get that. Let's try squaring it in the loop or something and returning it. So I guess I've now done the coordinate part, the part that handles coordinates. Now I'm gonna try to make a function that iterates to these coordinates and testing if they exist, if they exceed past the magnitude, the threshold that the numbers go towards infinity. So let's try making a function that counts the iterations. I'll make a constant called max iterations. If the number of iterations go past max iterations, I'll color it black and consider it inside the set. Let's make it 50 for now. I'm going to take an input C, which is your initial coordinate, and I'll assign a variable in which is the result of the formula C equals C minus 1. I mean C equals C squared plus C, where C is the result of the previous coordinate. Let's make it like that, lowercase, because I'm using for variable names. Set it to 0. And I will now I'll assign a variable in which I will assign it to C, because C starts out with the constant, and that's a coordinate. And I will make a while loop that until the magnitude of the vector that is resolved by the coordinate, if it does not exceed 2, it is not in the set. So, and that's, you return the number of iterations. And so I almost forgot, in this thing I have to do a magnitude equation, magnitude method. And all I do is return math dot square root this dot x times this dot x plus this dot I times this dot I. So that's the magnitude. Is basically like Pythagorean theorem. You take whatever is squared and you square root that. So when I loop while C dot magnitude is less than 2, I'm gonna iterate again. I think that is it. So I'm gonna maybe do that and increment number of iterations to 0. Increment number of iterations. And at the end, I will return the number of iterations. So let's try that. I'm gonna try calling test coordinate. I'm gonna try calling that and I mean call the number of iterations. Take that input as take this coordinate as an input and console log that. Zero iterations. Wow. Oh yeah, because this is 2. Let's try -1. 0. That's not good. Maybe I'll log something that some of the code here has been executed. Oh, it's not it's a function here, and I got 1 iteration. Now if I would do -1 0, I think that's in the Mandelbrot set, I'll get the max iterations. It came in it had a loop. This is not what we want. I'm gonna cancel this. Oh yeah, you know why? This ran infinitely because even if it went over max iterations, it'll still run. So I'll do an or and condition while the magnitude is less than 2, which is the condition where the values diverge from towards infinity, as well as the max iterations. So let's try that. I'm going to now enable this. I did some testing here because I thought this one was an error. And I will now try this out. So this one is in the set, and I should be getting 51. So that's 1 over max iterations. So if it's equal to max iterations, I'll not include that, and I get 50. So that's cool. So now what I'll do is get a way to color the Mandelbrot set with a formula that determines the color of function. So let's try that. I'm going to do an if statement here and first check. If it's greater than max, if it's equal to the max iterations, I am going to return black. So what I'll do is this function will return an object which contains the RGB colors of the Mandelbrot which represents a value in RGB. A JSON object. So if it's equal to max iterations, it's in the set, and I'll color it black. And or else, what I'll do afterwards, if it's not in the set, I'm going to color it based on the number of iterations. At the end, let's make it simple. And I'll just do it out of 400. Let's just do a grayscale. So the darker the lighter the shade of the gray, the more iterations it takes for it to be in the set. So the lighter the gray, more iterations it takes. And if it's multiplied by 200, think of it as a percentage out of max iterations, and times 255, which is the color of which would result in the color that you want. So white will be like nearest to max iterations, 1 times 255. So this is like the ratio, and times 255. So yeah. So what I'll do is I would now want to call these functions determine color and determine iterations. But our thing is that I'll need to extract the coordinate based on the row and column. So what I'll do is create a function that converts the row and column number to a coordinate because I think that's what you need to do. There are other ways, but I'll just do a short way, maybe in another video, in another part where I add zooming functionality. I will maybe change some of my code a bit. So I'm gonna create a constant offset. No, an offset. And set it up because I don't want the starting coordinate to be 0. I want the starting coordinate to be -2 in the x-axis, and I is like 2 and 2 and 0 and 0. So instead of that, I'll do this. It will just be canvas width halved, I guess, because I'll just subtract it. So I start at 0 and I'll just have it to make it an offset. So what I'll do is I'll now make it so you get a new coordinate. Because you convert from the canvas row number to a coordinate, and you have to have like a negative value at the start. And you divide by a certain number depending on the width. So let's say I want to get a resulting value of 2 instead of like 400. So it makes sense to divide by 200, and I'll try to, and that's how you do it. This is like a magic number. I should have like a constant somewhere. But yeah. So I'll just convert it and store it in a value. So converted x row input minus the offset divided by 200, it'll give you the x coordinate. And for the same thing for I, column input, which handles the complex plane, minus the coordinate offset divided by 200. So I'll just keep it as simple. Maybe I should do row and column offset. This make it better, because what if you want like a rectangular canvas and you somehow forget it? So let's rename it to row offset and column offset here. Converted x, converted I. So as I have made the function that converts from a row input to a coordinate, I'm going to now test it. I am going to test it to make sure it works. So I am going to 0 and 0. Convert to coordinate. Let's take an input of a row 0 and column 0, and I'll log that. Coordinate offset is not defined. I did not change my variable. Where did I add 51? 51. Column offset. Let's do row offset, which would divide the width by 2, and column offset. And it gives you -1 and -1. That's not what we want. The division should be 100 from, let's say it's row 0. The offset is 200. So it'll do -200 over 100. So now I'm gonna test that out, and it's -2, -2. Okay, so that's cool. As I've now converted, as I have a function that converts into row coordinate, and a column coordinate, a column input, not coordinate. I should now try to test it out. So what I'll do is I will now edit the color pixel, in which I will use the row and input, row and column, and return it. So what I'll do is I'll declare color results, in which I will pass in determine color, X column and Y column, and I will do color result.x dot red, color result.blue, whatever blue value, green, and then the blue value, in which we don't care, it doesn't matter because we're doing grayscale. And now I should be getting something. Oh yeah, determine color. Oh, it takes an input, a iteration. Never mind. What I'll do is I should have do a coordinate. Let's do that. This it should have done convert coordinate, which will give you a coordinate based on the row and column. And what I'll do is I will get the iterations. Determine iterations, pass in that coordinate, and I will pass iterations, determine color, using the number of iterations as input, and this will return an object of red, green, and blue, and use these values to color the pixel accordingly. Number of iterations at 88. There is an error here, which determine color. It should pass in number of iterations. And now, this is what I got. It looks blurry at first because my pixels are pretty badly resoluted. So I'm gonna create the pixel size as 1. Notice that in the previous video, I've called it a pixel. I should have explained that clearly at the beginning, but pixels are actually unit images, in which a unit image is like a little square. It can be multiple of one or more pixels or something. So if my image width pixel size is 1 or something, or I should rename it. Whoops. The unit image is what gives you the thing. So I need to remove the console logs because I already got the testing done. So, as of now, this is what I've got. You can see the Mandelbrot set. If I would increase the image with the canvas width, if I would do 800, let's make it bigger. Let's make it bigger like that. And I will take the zoom. It should be 400. I should have changed it. But the idea is, yeah, so this is what it is. It looks so cool, isn't it? You can see the main blob. It's called like a cardioid. I think a cardioid. It looks like a heart. And the side has some other circles and many properties of the Mandelbrot set. So that's really, really cool. I should have zoomed it a bit more, a bit less to see the whole picture. And yeah, look at that. Wow. And you can see at the left is a mini Mandelbrot set, and you got the main Mandelbrot set going on. This is a grayscale. So yeah. So before I end this part, I'm going to recap the pixel size. I should have explained it more clearly. But here, in color to pixel, I should have made it so it colors a unit image. The pixel in this case means unit image, in which a unit image can be 1 pixel in width or 10 pixels in width. It's like a square. It's like the whole canvas is made out of unit images. It's basically resolution. If I would do a pixel size, a unit image size of, let's say, more than 1, I'm going to rename it. Let's say if I would do 10, it's going to decrease the resolution. 20, even worse, like that. But if I would do 1, I get this. It's highly resoluted. So this is the Mandelbrot set. So if I would do, I could increase the number of iterations, let's say 500. It's going to take a while, but you got this now. It's less, you can see it's more black because it's harder to make it to transition from black to gray. And yeah, if I would do worse number of iterations, let's do 20. it will render a Mandelbrot set, which is not really well defined because the number of iterations is low. So let's bring that back up to 500. And yeah, this is it. This is the Mandelbrot set without zoom, unfortunately. And so, I hope you enjoyed this part. And the next part, which will be probably in a few days or maybe in a week, depending on how really I'm motivated in making this. It's kind of New Year's now, so. And the next part, I'll just add some zooming functionality. And yet, this is the Mandelbrot set. So, if you like this video, drop a like if you got your tingles. And once again, Happy New Year. So until next time, stay tuned for part 3, and peace out.